When we write out things in our lab, we should write your potentials as XX versus, SAG, or, silver chloride. We don't always do it. Sometimes we do. We don't always. In your paper, though, it is not acceptable not to write those references. At least it's got to make the methods. As I said, because almost everybody uses the same ones, it's not so critical. But it's, to be absolutely correct, you should just write volts. You should be right. It's 1 volt versus AG/AgCl. As I said, do we always do it? No. But somewhere along the line, you should give people a hint as to what your reference electrode is. So the ideal reference electrodes, then, right? Ideally, they don't change voltage with current running through them. Right? Because if you have something that's a reference, and over time, you have to run some current through it, right? Because you're doing a 2-electrode system, and your reference then changes voltage because something happens to it, like it oxidizes or reduces, or something else happens to it, then that's it can end up being pretty bad. Right, so your reference, if your reference changes over time voltage, then your voltages are going to change over time. And so that's not what you want, and so people try and pick references that are really stable. Again, we don't typically change the reference, although we tried one time. Megan and I tried a project where we're going to change the reference. Never really went very much of a place. Turns out, this is my hint of the day for in vivo electrochemistry, can't implant silver chloride into an animal long term and get the same potential out. But Reitman's group just published a paper that if you napkin code the reference electrode, it's okay. I believe that you get silver oxide, the potential shift in a manner. All I did to believe this was to go to my electrochemistry book, look at the table of potentials in the back, and find when that matched up for silver. That made sense. I believe it probably oxidizes. You get silver oxide. Now you're not measuring against silver chloride, you're measuring against silver oxide. The potential shift, you get about 0.2 potential shift. It would all work out just fine. They didn't prove that in that paper. I guess I should prove it. But they did show that a way to get around it. But yeah, so that's a problem though. I mean, so you think, oh, reference electrodes, no big deal. If we were learning to do long-term chronic in vivo studies, reference electrodes are a huge deal. It's hard to put something in the brain and have it stay there and keep the same potential. So that's reference electrodes. All right. All right, so we're going to start now with a little bit of overview of kind of potentials and that kind of thing. Okay, so in electrochemistry, they started from the beginning using reduction as kind of their prototypical example. So when they start in this textbook to talk to you about electrochemistry, they start talking to you about reductions. Now that's a little weird for our lab, right? Because we almost always do oxidation. Right, so you've got to get on board with the textbook that historically people looked at reductions and that they're going to start with a reduction. Everything that, like, if you look at standard reactions in electrochemistry, they're always shown as a reduction. So I know we love oxidation in our lab, but that's not how the textbook is going to come at you. They're going to come at you with reductions, and so you've got to be kind of looking at that. Okay, so they look and they say, what happens if we force an electrode negative? Right? So if we force an electrode negative, right, as the electrode becomes more negative, not surprisingly, right, we're able to then drive an electron from the electrode to whatever the molecule is that it's going to accept. Right? So if we go negative, an electron goes from the molecule, from the electrode to the molecule. That kind of makes sense, right? If you just think about the repulsion energy of it, that's what happens. So that process, right, that I just defined for you then is a reduction. So transferring electrons there. And if we were to define the electrode that a reduction takes place at, right, it's called the cathode. Okay, so if we take an electrode and we now force it positive, as it gets more positive, we might be able to drive an electron from a molecule, right, at the interface to the electrode. Right, and so that's the definition then. All right, it's more positive, right? I don't want to attract a negatively charged electron. So that's the definition then of oxidation. So when the electron goes from the molecule to the electrode, that's oxidation. And of course, oxidation takes place at the anode. I will now tell you the cheesy acronyms I learned in general chemistry, which I might have used in my class, but they're really good. Well, they're not really good at all, but I swear these like to help because they're so bad. My general chemistry professor taught us these like way back when. I still remember them. So to remember which one happens, like reduction or oxidation, and which one is the anode and the cathode. He taught us this one, and he says seduction takes place. I'll write it at the cat house. All right, it's cheesy, it's stupid, I don't know, but so that's supposed to be reduction occurs at the cathode. That you're supposed to be able to remember that. If these do nothing for you, they do nothing for you. The other one that I think is more popular is this one, which is Leo says GER. So if a molecule, but you got to remember, you got to define, that's the only problem with this, if a molecule loses an electron, that's an oxidation. So that's the Leo. And if a molecule gains an electron, that's a reduction. That's the GER part. So Leo says GER. I am pretty strict. If I hear people misuse these terms in response to their data, I will correct them every time. I'll correct you in group meeting, I'll correct you in Monday meetings, I'll correct you in our talk, because you cannot misuse these terms and sound like you know what you're doing in electrochemistry, right? I mean, the second that you get up and try and point to your oxidation peak and call it reduction, right, you've lost all respect from any audience, and I won't let people misspeak. And sometimes, we all misspeak, I know, but I'm going to correct you every time, because I can't let you do it in good faith, kind of thing. And so if you struggle with oxidation reduction, then you have just got to, figure it out. You've got to figure out a way to remember what it is, which one's the oxidation, which one's the reduction. You've got to have this stuff backwards and forwards. You can't get it wrong. Again, it sounds like any person who knows what they're doing. Okay, so let's look at a prototypical example. Right. That's great structure. Okay, this molecule, dopamine. Again, you're getting a specialized class. It's not good. I'll throw in something. All right, so this is dopamine, right? And everyone in the lab should be able to write the structure of dopamine and the oxidation of dopamine. And sometimes I think the problem when people can't do this stuff at their orals is because they simply have always cut and pasted it from somebody else's intro slide, and it's on that intro slide, and they never seriously sat down and wrote these things out. So if it was me, every molecule that you do electrochemistry on, you must have memorized that molecule's structure and how to write their electrochemistry reactions. So we'll do dopamine today, but you must know what they are. And you must be able to write them from your brain. You can't rely on just, oh, I'll put them on slides. You know, I mean, if you do 20 molecules, maybe you could put some of them on slides. But the, the main ones that you do all the time. So if you're an adenosine person, you need to have memorized the adenosine thing. If you're doing octobene power manager project, then you need to have memorized that. You need to have memorized the molecule that you're looking at and be able to write out its oxidation and reduction reaction. Now, of course, dopamine's the easiest one, right? And I should make this so it goes back and forth. All right, so we start out with dopamine, right? And it goes to dopamine orthoquinone, right? And it loses, right? So to go there, it loses 2 electrons, right? So that's the oxidation. So again, I don't always love the Leo says GER unless you tell me what has to lose an electron. It's the molecule, right? You could look at it from the electrode side. So dopamine loses 2 electrons. Now, you gotta have charge balance. And again, if you've never thought about this, sometimes we just throw these protons in, or people don't think about the protons very much. It loses also 2 protons, right? These 2 protons, right? They go away. But if you've never thought about it, you should think about it. It loses protons too, and that's part of the charge balance. All right, and so when we go back the other way, right, then dopamine orthoquinone, which we usually write as like that, right, then gains 2 electrons, right, and that's our reduction. So those are the reactions, again, everybody in the lab has done. That's done in electrochemistry. And you just got to have them in your head. Any reason that I harped a tiny bit on the protons? Do they matter at all? Why would that matter? Does anyone know what that makes this reaction? It makes the reaction. Well, it's charge neutral, which means I did a good job balancing it. It makes this reaction pH dependent. Right? So anything that's going to produce or create protons, right? So the fact that they're there makes this reaction pH. And again, we don't normally think about this because most of us run right around the same pH, right? It's either 7.4 or 5 or maybe 6.5 kind of thing. But it is pH dependent, and you get some funky effects if you go to more extreme pHs because it makes it harder. Like if you were in an acidic pH, right, it'd be harder to do this reaction because it wouldn't want to produce those protons, right? They'd be inhibited. So again, everything you know about charge balance, pH, whether or not you're going to want to make more protons exactly, exists. So this is a pH dependent reaction. And there's lots of papers out on there. It's just not the kind of papers we typically read because they're not FSCD papers. Well, there's 1 or 2 on FSCD that'll mention this proton thing. But I'll just throw it in there. Let's look at it. Okay, so now let's talk about conventions of what should be positive and what should be negative. Right, so when we draw a cyclic voltammogram in our lab, we draw it like this, right? Where, I don't know, let's make that like 1.0 volts. This one is like minus 0.4 volts, right? And that's dopamine. And so in our lab, right, this is the oxidation peak, and this is the reduction peak. But if you picked up the textbook, you may have noticed something. They don't plot things like this. Traditional electrochemistry has for years plotted things like this, where they would plot the negative numbers over here and the positive numbers over here, because they liked reductions. And everything that's a reduction they want on the right-hand side because they wanted to talk about reductions. And if they were to write our CV of dopamine in the textbook, they would write it like this. Where this then would be the reduction peak. Notice it's positive current now. And this would be the oxidation. in some ways, this convention, although I'm not sure about the switching the axes to the right-hand side, quite frankly, makes sense. So if you're doing an oxidation, you know, your electrode, right, is accumulating electrons, right? Your molecule is losing them, they are going to your electrode. So it makes sense that in the beginning they define that as a negative current, right? You're getting more electrons, that's negative. But that's why the textbook does it. It defines all reductions as positive, all oxidations as negative current. Again, not voltage now. I'm not talking voltage where things happen. We're talking about current things. So you just got to know that there are different conventions out there. And the first time you read a paper, you got to think to yourself, what convention are they using, right? If you're reading our FSCD papers that are kind of in our field, most of them use our techniques. But I'm going to tell you, when I did grad school, we did this. So any paper before about 2003 is going to look like that, even out of Whiteman's lab. Everything I published as a grad student looks like this and not like that. So about 2003, he decided he would switch, and they claim that this is the, what is it, the IUPAC? You know, that's the way the IUPAC says, you know, come on, especially the engineers were trying to do it right. IUPAC said you should do it right, and I don't know why the has to do this and they'll flip it. So we do this now, but the textbook's going to do this, and if you pull up old papers, they're going to look like this. So I want you to know that. So what do you need to do if you're like, oh my gosh, that's so confusing? You know, really, if you take something and it looks like that, basically to put it in the old convention, you know, you just flip it upside. If you take the whole paper, flip it 180, you'll be looking at it the way you're used to looking at it, and you know, vice versa. So if you take an old paper and you turn it 180, your CV would look like it does now. But you gotta know. I know it's confusing. I'm sorry the field changed conventions, etc., etc. There may be still, even in the FSCD field, I'm not sure about it. I'm trying to think whether engineering microscope has switched or not. There may be people who still do this. You can't let it throw you off as you're reading the paper. Again, it's my warning. So when we read it, and we're going to go through the textbook then, we're going to have all reduction currents are going to be positive, and all oxidation currents are going to be negative. That's just the way the textbook's convention is. That's opposite from our lab and what we use, but again, it's something you kind of have to know. You should have that kind of thing. Okay, so if you were to take a reaction like this, there are tables out there that will give you standard electrochemical potentials. E0 for reactions. Anyone know the E0 for dopamine? Come on, haven't I said it for 0.2 sounds good enough. It's probably between 0.15 and 0.2. Right, so if you were to look it up, again, you'll see that I don't have some grand knowledge of like everything to the third decimal place. I'll take 0.2. 0.2, you gotta know that, right? Because so many people get confused and say the oxidation potential for dopamine is 0.6. Right? You say my peak occurs at 0.6, so that's the oxidation potential for dopamine, but it's not the oxidation potential for dopamine at all. Even with FSCB, it's just because you're going fast. So it's much lower than you might actually think from the experiments that we do. So anyways, we'll talk about those a little bit more. Okay, so that's dopamine. We all love dopamine. Again, not one in the textbook. So you'll see how I kind of go through the textbook and then I take it aside to do what we do. Okay, so let's start for a little bit and talk molecular orbitals. Okay, so let's talk molecular orbitals for a minute. I can just tell you that professors sort of love this kind of diagram if you're going to do it in your oral exam. So, you know, of all the things, you know, if you're a chemist and, you know, they ask you a question about oxidation, you start throwing up molecular orbital diagrams, they just keep that stuff up, right? So let's say, you know, Right. This, I guess, is my LUMO. So I have my electron, right, that starts in a reaction. And then this is, so on this side of my diagram is my electrode, and on this side is my analyte, whatever I'm trying to do, right? And this is its occupied electrons, right? And so this would be I was like, that didn't sound right. This should be the LUMO. And it should be the LUMO. Highest occupied molecular orbital, well, this would be its LUMO over here. All right, and that's the lowest unoccupied molecular orbital. So let's go like that. All right, I love the whiteboard. All right, so we have, this is the energy then over the electron that we want to transfer over in the electrode. So let's start doing a reduction. So if I were to start doing a reduction, that means I would be making this more negative. So as I go up on this diagram, it's becoming more negative. And so, right, as this starts to go up in energy, eventually, right, as I become more negative, it would be up here. Now this has more energy than the LUMO, and so it can transfer the electron over there. So that's the electron, that's the molecular orbital picture of electrochemistry, what's happening. It's not so hard, right? This has to get above the energy that you would, to fill that, and then you can transfer over, right, into the vacant molecular orbital. So, right, this is an example, then, of a reaction that would look like this, right? Where whatever A is over here, my analyte plus an electron goes to A minus. Remember, we got to remember about charge, right? I don't have any other charge to balance that, so this one would be minus. It would get the electron. All right, so then oxidation is not so hard. We're going to still have the electrode over here, my analyte over there. We're going to start with an electron. And so, oops, what am I kidding? Right, so now let's think about oxidation.